next couple lectures, we're going to do kinetic modeling with PET, and I hope on the website we've given you access to 2 different documents. One of them looks like that. I'm part of a group who teaches a course once a year that we take. It's a 2.5-day course on pharmacokinetic modeling. It's usually associated with a conference right before a while. Last time we did it was back in May in the Netherlands. This is our manual. It's something we've worked on over the years. It can still use a lot of work, but it's a lot of the different kinds of ideas. So that would give you a lot of supporting material. I think I also gave you a copy of a book chapter that I wrote a couple of years ago on tracer kinetic modeling. So hopefully those have gotten posted. I think I sent them to you, Raquel, whether they're posted and available for.
Yes, I think I have it there.
Good. Okay, so they're hopefully available for you to use as a good reference. Supports a lot of the material that we have. There's lots and lots of references, but at least it'll be something there. So we're going to take, we did the basic compartment modeling, simple math, linear systems yesterday, general. Now we're going to turn it into how we work, specifically radioactive tracers, well, mostly tracers like that, how we can use them to radioactivity modeling. So we said this yesterday, we talked about tracers and trace C. The naturally occurring compound is the thing we're being traced, the trace C, and we hope to follow it. We hope that is detectable, obviously. It's pointless if it's not, that it doesn't perturb the system in any way, and that ideally it's indistinguishable or marginally indistinguishable. We'll get into that in particular. Okay? Now the tracers can be lots of different things. They don't have to be radioactive. That's something I've spent my career on. They could be chemical if we have sensitive enough, or stable isotopes, things we can measure, or if it's an MRI, we can measure them if they're paramagnetic, or fluorescence, or you name it, any way to be able to do that. One thing that has certainly changed over my career is the sensitivity of some devices to be able to take measurements of non-radioactive molecules. It's gotten very, very good. UV, LC mass spec, so not even stable isotope, things like that can be measured well. The trick, of course, is to be sure that that word is still good, because when you're measuring very, very small quantities, you want to be sure you're not affecting the system. Okay? And of course, we want them to be similar. So one classic example would be to take a molecule like glucose, make it radioactive, old-time ton with something like carbon-14, not something we inject in people, but we can measure. In this case, it is identical. The presence of the 2 extra neutrons in carbon-14 compared to carbon-12 has no effect on the chemical reactions. More often, we tweak the molecule a little bit. We make it an analog. Now that means it's not an absolutely identical molecule, but we've done it in a clever way so that it doesn't change its fundamental characteristics, or it changes them in a way we want them to. So when we make an analog of glucose, like fluorodeoxyglucose, the things we want to track are still sensitive to it. One thing we have to be worried about is, does it affect how it interacts with proteins and enzymes in the body? We'll talk about a little of that coming up shortly. Okay. So I've added a couple slides here if you're looking at there before we wanted to start thinking about biological reactions and chemical reactions. Starting from the kind of a very fundamental thing, and you all learned this in chemistry years ago, is if I've got a chemical A, something reacting with something to produce something else, A plus B becoming C at some rate, I could write down the rate of reaction. And the rate of producing C is the concentration of A, the concentration of B times this rate, constant K. And to think through these units of K, it's kind of funny, because if, say I have a concentration unit here, and a concentration unit here, and a concentration, that's time, K has units of inverse concentration, inverse time, even uglier than the rate constants. If I have a reversible reaction with 2 rates, K1, K minus 1, I see the net production, K1AB, and the net release back, K minus 1C. Basic stuff, fundamental chemistry rates of those things. Now in biology, many of your reactions have enzymes, proteins, to make them work. And so you have a standard form would be that I have a substrate, S, the molecule I'm metabolizing. With an enzyme, they will produce a complex. They'll come together at some rate. The complex may degrade back to its original forms, or may go on to produce a product, P. So I've got a substrate producing a product aided by an enzyme. And the enzyme gets recycled. So we use it, modify it, put it back. And for there, we could write down a combination of those equations that we'd see how the rate, how the substrate is produced or retrieved. The complex is pretty complicated. How the enzyme is used in multiple ways, etc. Simply by, this is a bookkeeping exercise, that every time we have a step, we have a k-1, we lose C, so it's negative here, and we gain it, S, and we gain it in C, positive. So just checking it. Now the other thing we have is in any real system, you have so much enzyme to start, we'll call that E0, and at any given moment, the enzyme is either in its available state, E, or it's complex to the substrate. So we know that E plus C is fixed. We also know that we start with a certain amount of substrate in the system, unless we're adding more, and as that converts to protein, the total of the substrate plus the product has to be conserved. So we have these two things. We've had 4 equations that reduces it to 2. And the thing that was developed a long time ago by friends Michaelis and Minton was that they recognized in biological systems, these complexes turn over fast. They're ready to recycle over and over again. What that means mathematically is that the rate of change of the complex that quickly reaches its state is basically 0, no change. Equilibrium state of the substrate complex. Not the substrate, not the product. That's changing gently over time, but that we're keeping this rapidly turning that over. Okay? That the kinetics of this are fast. And if so, you can do a little algebra, you can set this equation to 0, plugging these things in, you can get a result for the complex. And what you will end up with is this equation that the rate of change of the substrate has this interesting form. It's a function of the substrate, but it actually appears in 2 parts. Let's graph that. Let's graph the rate of reaction as a function of the substrate. Oh my, it's over here already. How about that? Look at this. This will be positive. This is, or actually this would be the minus of the substrate or plus of the product. That as the substrate, if I have no substrate, I produce nothing happens. That I have some maximum speed. We call that V sub m, m for maximum. Maximum velocity. And then we're going to characterize this that there is some concentration, which we'll call Km, at which we are half maximum. Okay? So at S, if the substrate concentration is equal to this Km value, we are at half maximum velocity. Nice, very simple curvilinear thing. Over the form, again, here we're talking about it as Vm S over Km plus S. 2 variables control the system at steady state. Okay. Now what this is telling me is that I have some process that is saturable. Okay? In other words, I add more, if I double the substrate, well, initially my rate doubles, but eventually it flattens out. And it flattens out because I start to saturate the enzyme. Saturable process. Now, so here's that graph right again, that solid line. Okay. And this is that relation of that velocity, the maximum velocity, in this case C for the concentration. Now, saturable, that sounds bad. That sounds like not a tracer. So what happens if we add a tracer into the system? What if we have glucose? So imagine this is the glucose concentration curve, and we have glucose in your body, and you're metabolizing it, and we're somewhere on this curve. At this moment, did you have breakfast? Your substrate concentration might be high. Did you skip breakfast? Your substrate concentration might be low. You're going at some point right now, driven by the glucose level in your tissue. Let's add a tracer. We'll put the tracer, we'll make a little star for the tracer. It's sparkly. We can see it. It's scintillating, perhaps. Okay? And which is, say, it's also a substrate for the same enzyme. Now, the molecule might be a little different, a little tweak different. So we're going to say that it's got a little different. I think I've overlapped it. Instead of the VMs, we'll call them VM star. The maximum for the substrate is a little different. The Km star is a little bit different. If you write down the differential equations and solve them the same way we did it, you come up with this velocity. This is the rate of the consumption of my tracer. Okay, I have it as the maximum for that rate times the concentration. I've got a couple different Kms. This is for the substrate. This is for the tracer. Again, a molecule that's slightly different. It's pretty ugly. Now here's where we apply a tracer assumption. That if the concentration of the substrate, of the tracer, with respect to its Km, its occupancy, it's much, much less than 1. I mean, or practically, all we have to really say is and I'm giving tracer much, much less than its halfway point, its Km, then this term is negligible. And if that term is negligible, this gets much simpler, because this C star is scary that if I have a rate of change, I've got C star in two places, it makes it nonlinear. If it's gone, poof, it's linear. We've just defined a tracer. We're working at tracer concentrations if the concentration of our substrate is much less than its Km. That we're working for the tracer way down here. Now the other molecule, the trace C, could be happily occupying after the enzyme. You name it. Okay? And if this is the case, okay, so that means that if that's the case, the reaction rate is linear in the tracer concentration. So we measure that, that's great. And then a subtlety would be, well, one thing we want to also worry about is, well, this has the concentration of our trace C, glucose for example, and if we want this to make the differential equations really easy, we need that to not change during the experiment. We need that to be constant. Okay? So if the concentration of trace C is constant, it's in steady state, then the rate is not only linear, it's a constant. Hooray, we've got differential equations with constant coefficients. Good stuff. Okay? Here's a little reaction. If we happen that the tracer and the trace C are the same, they have the same VM, then it gets a little bit simpler. All right, we've just done this for enzyme reactions. Let's do it for binding to receptors. What's that mean, binding to receptors? That all over your body, your brain, all over you, specific proteins, often sitting in membranes, ready to reach and receive molecules to react and produce changes in cells. It could be to send nerve impulses. It could be to have hormones affect portions of your body to change or correct how you're releasing all sorts of hormones. Okay? So let's look what those equations look like, and you know they're pretty similar. These are kind of reactions, okay? So it could be that I'm going to have a reaction rate, that I'm going to have a ligand, some kind of, I'll call it free, let's go, and it's going to react with a receptor that's available. You want to call it B, yeah, let's call it B, and that's going to produce something that's bound. So we say free plus a receptor goes to something bound, and that can collapse back. We're not changing anything anymore. We're just finding bound and free. So we could write the equation this way. So we have a total amount of receptor B max. At any given time, some of it might be bound. That would be B star. That would be what's left. So the reaction is the same kind of law of mass action. This is called an on rate, binding on rate, times the product of the two. The available receptor, total minus bound, times the free. And then the off rate would be the clearance rate. Similar math that we've just done before. Okay? So this available, we would say, okay, what's the, that available is the amount that's just not occupied at any given moment. So for example, right now in your brain, you have various receptors. You have acetylcholine receptors, you have dopamine receptors, you have serotonin receptors. At this moment, there's a little bit of each of those neurotransmitters hanging around, occupying some of them. Might be a lot, might be a little. Okay? Now this equation, as I've written, is ugly because it is nonlinear. This is my state equation. I'm going to have a differential equation for free and bound. That product is trouble. Now, if we were at equilibrium, we could do some equations. We could derive what the rates would be, and we could look at how the bound would relate to the max, and we get a relationship like this. Let's look at that one. Let's see, that one would say that the amount bound at equilibrium, we got to equilibrium, as a function of the free concentration. Okay, so I've got some maximum B max, so I have some, and then it's of course the same equation with different letters. And the maximum is B max as opposed to B max, right there. And we're calling this KD, another K, this is called the dissociation constant, the concentration that half saturates. Okay. But this is, again, nasty nonlinear stuff, not to mention possibly dangerous. If we gave a tracer that started saturating some of your receptors in your brain, we could kill you. We could produce, we had some cases, there's cases known where something was very, very effective and it produced the delusional state. So, what if how much ever we label, the part that we label with her is much, 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 much less than the concentration. Let's go back over here again. Here's that term. I've got that bound, but if this is much, much less than that, then this collapses in exactly the same way. And And the differential equations, again, become linear. That is, the rate of change there, there's no multiplicative factor there. Okay? If I write it with a competitor, just like we did before, here's what the equations look like, but now it's the total concentration minus the bounds. And this on rate that we see times the free concentration is a function of the total available. So this is where we need to be if we're going to be a tracer. We need that the amount that we bind with the radioactive molecule is much, much less than the available receptor. Okay. Now we have low occupancy of the sites. Now yesterday we were touring the Winter Palace, and that brought to mind this slide because this would be a low occupancy state that we'd have here out there on the lagoon, and in some parts we had very low occupancy there, but other parts we had much higher occupancy. And so this is the point where this would not be tracer conditions, but this would be tracer conditions, that we're not occupying that, just in terms of whatever the available sites, in this case, the power plants. Okay. So to summarize these ideas, the biological, mathematical biology ideas, underlying everything we're talking about, enzyme reactions, binding to receptors, there is nonlinear reaction rates, like these curves over here. If we're using small concentrations of our molecules, our tracers, they are truly tracers. That means that their concentration is small with respect to their binding constants. They're not changing any occupancy of enzymes or receptors. And at that point, the differential equations become linear in our radioactivity concentration. Then, if the underlying molecule isn't changing, the glucose concentration for glucose reaction, the amount of dopamine for your dopamine receptors, then this K of T becomes a constant. And life gets very, very good. We get to be linear models, constant coefficients. We have a chance to do it. This is the assumption we make every day when we're trying to use a radioactive tracer or any tracer in doing this. This is why this is hard for people, say, at MRI, who claim to do this stuff. They have to be very, very careful that they're not changing that saturation, that those equations work. Now, often they'll just do it, and it doesn't mean they're not getting something useful. It could be that when they're going to make something, a measurement at micromolar levels, it really will depend on where they are on the curve. You know, if they're not too far off, this might be fine. This might be one of those acceptable errors. This might be one of those bullseye errors that they're still very good, they're just off a little bit. As long as they don't get to the point of saturating that tremendously. Or something that's going to have different amount of saturations from one person to another or one day. Okay, now let's take those ideas into PET. Same thing can be true with SPECT. There's been a lot more of this done in PET than in SPECT. Why is that? Why is that? Modeling, you know, nuclear medicine modeling, you're going to get about 95% of the papers are going to be PET compared to SPECT. Why is that? Right, so PET started that way because we thought, we claimed we were quantitative. There's lots of dirty little secrets in there. But probably a bigger one is that one thing we needed early on was to be able to do dynamics and be able to collect that more easily. Not that you can't do it, but it was kind of the thing that the PET was so dedicated in the research environment, it got a lot easier, whereas SPECT was being used clinically, it was harder to do. Probably more importantly was how long of a time do you need it? That by definition, the shorter-lived isotracers of PET, they have to be designed that you get the information you need in a reasonable amount of time. With SPECT, you didn't have to necessarily have that. You had 6 hours, you had 13 hours, you had plenty of time. Nobody is going to scan somebody for 6 hours. That's not good. If I can scan for a half hour, an hour, top 2, maybe, that's a little bit. Okay. So this I think you know. What's the picture of this? Let's do it there. We're going to start with a cyclotron. We're going to make some isotone. We're going to hand it to a chemist who's going to produce a radiopharmaceutical. I always like to use that long word. It's a radioactive drug. And every day when we do this, somebody is making a drug, injecting it in a human being, and they're not testing it for weeks or days. They're often testing it for minutes to be sure it's safe and effective. How do we get away with that? How safe can we be? The trick is that tracer thing again. When we give a molecule to a human being, even in a research environment, if we give a lot of material, it might be 10 micrograms. Very, very small. If you take an aspirin, something like that, you're taking 50, 100 milligrams, 1,000-fold excess. So there's a huge safety margin. in what we do. Okay, we're going to inject the subject, and if we're going to do a kinetic model, we may follow images over time. We're going to have a 4-dimensional data set, ideally all quantitative. Okay? Now we know that doing this modeling and doing it with pets very good because we can, by using these classic tracer methods, we can really turn this and use these simple ideas, classic like laws of mass action there. Since our isotopes are nice, carbon in particular, fluorine are easy to add to biological molecules. The half-lives are short, so we can do repeat studies. As we said, we're pretty quantitative and getting down to good resolution, and then we can start applying some of this math to turn that into physiology. This is a really rich place to do, especially when every new molecule and every new organ and every new species gives you an interesting question that you can ask or something you can optimize. So we're going to get some dynamics over time. We're going to add that information into the model. We're usually going to give it some other information, the input function, measured somehow or implied somehow, some pile of assumptions, and that's going to let us read out, take radioactivity and turn it into some measure of physiology. All that will be there. And this could be an algorithm, equations, an unreleased model, computer program, all the things that go. All right, so what are we trying to do so in terms of, we have 2 thoughts we do as we're trying to model. I mean, our goal is to use the measurements of radioactivity at the regional level, at the pixel level, and ideally, if life is good, get an unbiased estimate and a low noise, precise estimate of whatever we're after. That's kind of what we'd love to be able to do. Do the best we can with the data, and whatever it is we're after, blood flow or metabolism, whatever our molecule is targeted for. That's kind of almost, but the other half we can say is, can we do it better or faster or cheaper? Kind of classic engineering. How short can I scan to get the information I need? How little dose can I give to get it? I talked about measuring input function, and how do we do that? Can we do that from the image, or do I need samples? And then depending on what I'm trying to do, a clinical read, a research study, how do I maximize the signal? How do I tune in to say, if I'm looking for a certain thing, what do I need to do to most maximize it and not make a mistake? Okay? All right, so let's back up. Start this from a different perspective. Here's some images. This is from a tracer. This tracer is called AFM. This is a serotonin transporter. Serotonin is one of the neurotransmitters in your brain. It's particularly implicated in a number of neuropsychiatric diseases, including depression. In the States, it's very common in the West to be prescribing SSRIs, Prozac, Zoloft, etc., for people with depression. They've run marvelous things. I don't know how common that is in here, if that is growing. Okay? All right, so we've made a radioactive Prozac or Zoloft, and here's some images. I've colored these in 3 different colors. You can take your pick. This is a slice of the brain, front, back, probably left, right, a transverse slice, if you slice this way. And what we've done is choose 3 different times after injection. Here's the first 10 minutes. Here's from 40 to 60 minutes. Here's from 90 to 120 minutes. Same images, of course, this is from a scanner. It's from a real human being. It's just a bunch of numbers that we've color-coded. And bright here is white, and bright here is white, yellow, dark is red. Here we've got different colors. What do you see? What do you see in these images? Can you tell me anything you noticed? Anything. Real simple. Whatever comes to mind.
Okay.
Sorry?
They have okay up there.
Right. I'm just trying to think, just independent of that, I mean, do they stay the same? Do they change? Yes, they change. Is that good or bad? That they change. The images change. This seems to have a widespread activity. This seems to be focusing in that region. Take your choice how you like to view that. Is that a good thing that they're changing? Are they supposed to change? Why are they changing? What's going on? What is it telling you? Is this telling you something? This molecule is designed to bind to a particular protein, a particular transporter, thing that sucks up serotonin. What is it telling you about that? Is it telling you where that molecule is? Is it telling you that? Where do you think there's a lot of that molecule? Is it everywhere? Is it all in this area? This is telling you that a lot of it's there. Unfortunately, this molecule was not smart enough to know that when we injected it, it shot up your carotid arteries and went to your brain. It first went everywhere. It went everywhere. This is a picture of your image. The bright areas are called the gray matter, the cells of the brain. They have higher blood flow. The darker areas are white matter, the cables of the brain, lower blood flow. Almost every tracer looks like that in the beginning because every tracer just goes and arrives in the brain. And the trick is what happens when that molecule is there. How does it interact? In this spot of the brain called the raphe nucleus, there's a lot of that transporter, and it's stuck. In the rest of the brain, on these levels, there's not much there. It went in and said, oh, no reason to stay, I'm leaving, and left. Okay? And so slowly over time, we built contrast. Okay? Initially, very little contrast. Okay, so say you've been charged to decide a method for analyzing studies. You want to study a set of population of people who have depression compared to matched, very careful controls. What do you do with this data? Well, this certainly looks like it has a lot of the information. Maybe I just want to analyze these late images. And that might be fine. But there's certainly some information here. I mean, there's some contrast there. Maybe not much here. How do I want to use all this information? How do I put it all together? I mean, ideally, I'd chop off their head, take out the raphe, measure how much receptor that would be. I want to do that mathematically. All right. So let's take that down. We're going to zoom down. Sure.
Sorry, I think I missed the... So these three rows of images are same images?
These are exactly the same image in 3 different color schemes. Take your choice. Whichever you want. Each one is the same, but they're different times.
Oh, I see.
The times are on the bottom. How the evolution changes. Take your pick on how you want to look at it. All right, so let's zoom down. Imagine we are zooming way, way down into a capillary. Okay? So I have arterial inflow, and I've given a tracer X. And then it might flow out by the vein. Okay? I could make a tracer where that's all that happens. Can you think of a molecule that might just stick in the blood? Anything come to mind? Very simple molecule, something we could make, you know, with the isotopes we have. Well, something that we hear in the States is people suffocating because they fall asleep in their car running in the garage in the winter. They suffer from carbon monoxide poisoning. CO. And if we label CO, that's been done, it sticks very, very well. It blocks all of your hemoglobin. It beautifully sticks in the blood, and that would be it. That would be our molecule. We labeled CO. Okay. Now we've done, the PET studies have been done with CO for years, and we haven't killed anybody. Why? It's tracer levels again. We're binding, but there's very, very little of it. We're not out. Now usually we're doing something more interesting. Usually we want it to cross into the tissue, and maybe it'll cross back. We might make a molecule very simply that that's all that it does. Goes in and goes out. What might be a really simple molecule that might do that? What's like the simple, really simple molecule? Well, oxygen's actually more complicated because oxygen gets metabolized. Okay, it gets converted, it gets used. It goes in, but then something happens to it. Even simpler than that. Water. We make label drink water. That's all it does. Goes in, comes out. Water's everywhere. 55 molar. Now, usually we're doing something more interesting than that. Usually we want it to bind to a protein, like that one we just talked about. It might just bind and stick, or it might come off. It might go back and forth reversibly. Or maybe we want to metabolize it. It's phosphorylated somehow. And that may collapse back, or that may clear. And now you start imagining all the things that we could do. This is what we were alluding to yesterday when we said, how do we start constructing a model? We think about what's going to happen in the biology, and we design the molecule with something in mind. We may design it to bind to a particular site, something like that. Okay? So we're going to characterize these places, which are physical or chemical, of the compartments. It could be the physical space. It could be intracellular or extracellular. It could be this biochemical space, free or bound. It could be a metabolic space. And I'm calling it space, and it's very amorphous. It's not a physical thing necessarily. It could be physical. But where we talk about all those compounds behaving the same way. And as an aside, if you read any of this literature, people get very bad at how to count. That in the PET and SPECT literature, the blood does not count. We're talking about the tissue counts when we talk about this mathematically. It gets very confusing. The old literature, the blood always counted. All right, so we might draw a model like this. Here's one for one of that same agent. This is going to be in the blood. This will be in the tissue. We might have our, we'll call it a ligand, another word for a tracer. It's going to go into the tissue and can clear out. It might bind to a receptor and clear back. It might also bind to other stuff. A lot of these molecules are kind of pretty sticky. They just go to fat and proteins and things. So this would be happening like everywhere. This would only be happening where those receptors live. Okay. Now the thing that's tricky, and I'm really waiting for Raquel Roger to build me a better system so that I can, unfortunately, in the past, can't differentiate which is which. All I see are the counts. So I'm measuring this total counts. Now you may see the way I've drawn my box. It isn't because I have bad PowerPoint skills. We carefully drew the box because there's also blood in the tissue, and some of what we measure is in the blood. Mostly, hopefully, it's tissue. So that's what our signal is going to be. All these compartments, a little bit of what's going on in the blood. All right, so that's the starting point. So what are we going to do? We're going to start with a few things. What are we going to do? We're going to talk about the input function, time course of our radioactive tracer in the blood, because we're going to mostly deal with all organs where everything comes from the blood. That's good. The tissue response, of course, will be what we measure from the scanner. It's going to measure all the compartments, the sum of them. Can't tell them apart. And we'd like, in principle, to be kinetics to be able to figure that out. We're usually pretty bad at it. Okay? What's nice is, if I can measure the blood or infer it some way and then measure my organ, I don't care what's going on in the rest of the body. I don't care if the liver is clearing something or not, because I can see that it's in the blood. But it's really, really important to think about that input curve. Again, if I had identical syringes and I injected it in all of you, you would all clear it differently. That would mean the target organ, say the brain, would see a different amount for every one of you. And if I just believed the activity in the brain meant what we were seeing, we would be learning more about your liver and your kidney and claiming it was going on in your brain. Okay. So what can we measure? Well, if we have that model, we're going to assign a number, a rate to those things. And that's what we can do. This is where it gets very unexciting for people to say, you're going to spend all this math and all you're going to do is get a bunch of numbers. It's usually the way that works. All right, I mentioned assumptions. We're going to need some assumptions. And some of those will be pretty simple. Things we said yesterday, flux between compartments is proportional to the source. It's a linear system. Everything is well mixed. Same thing. Steady state. Nothing's changing. Nothing's changing in my endogenous. The traces aren't changing. Tracer concentrations, the big key one. Usually we're going to assume we know the input function. That's a little shaky usually. We actually measure it. Okay. And one other subtlety, we give these molecules into your body is very good at chewing things up. And it chews up what we inject and produces another molecule or another molecule. They're all still radioactive, but sometimes we can't tell the difference. It's really important for us to know what happens to those metabolites, the radioactive metabolites. Do they cross back into the tissue? Do they confound my signal? How complicated would it be? A lot of PET modeling has occurred in the brain. And the reason is the brain has this wonderful thing called the blood-brain barrier. It keeps a lot of junk out of your brain. It keeps your brain nice and clean. It does a really good job keeping a lot of the metabolites out. Makes the modeling simple. So this is one where, I view it that God gave the brain to modelers because it has as a blood-brain barrier, it keeps out the metabolites, and it doesn't breathe, and it doesn't beat. It's great. We've started working below that. It's scary. Okay, so we'll come back to that. All right, so what can we measure? Well, now it's all depending on what our tracer is designed to do. Whether we're doing blood flow or blood volume. We might measure blood flow with a tracer that just goes in and out of the tissue, like water. Or blood volume with a tracer that sticks in the blood, like carbon monoxide. We might be able to measure the permeability, how well it goes in. Or even in principle, a single metabolic step. And if everything was perfect, those are true, but usually when we switch hats from our biology hat to our engineering, physics, statistician hat, we say, well, things are a little shaky. Maybe we shouldn't ask for so much. Maybe we want to ask, what is the data telling us? What are the statistics? And we may look at a net rate, or something called a volume distribution. We'll talk about all those as we move to specific examples. That's part of the things we want to do. It's very, very easy to write down equations and get numbers. Do they have biological meaning? Not good. Okay. All right, so here's an example of a data set you might start with. Here's some measurement in the blood. This is in the arterial blood. Come to that. Here's a measurement from a PET scanner. This is each of these values is from taking a reconstructed image, a region of interest value, extracting. This is clearly old data. I have the old units, nanocuries per cc there. Okay. So this is kind of what I'd be handed to say, okay, how can we model that? All right, so now we could do this blindly. We could say, I don't care what the data is. I could try this model, I could try that model, I could try that model. And we could try to say which one is most consistent or describes the data best. Tomorrow, we'll do a lecture on estimating parameters, and we'll talk about how do we pick or compare one model or another just from the point of the statistical quality of the fit. But it's also good to back up with the biology of what's your point, what's your question, and what might be the smarter model. For example, it might be that you can say, yes, this very complicated model describes the data better than this model, but it might be that this model gives me very noisy data. Think the dartboard again. This one might be accurate, but variable. Maybe I'd be happy with something that's less accurate, shifted, but more precise. And if I'm good about thinking about how are things right or wrong, all that time. Okay? So, same equations we did last time, we'll change the nomenclature. Typical nomenclature, capital C for concentration, lowercase p for plasma. That's the concentration of, what's plasma, by the way? It's nothing to do with high energy physics. What is plasma? What is plasma? P-L-A-S-M-A. P for plasma. Anybody heard of plasma before? Pumping in you right now. It's part of blood. It's the liquid in the blood, not the cells. Everything but the cells, because that's where any tracer is going to get out from the plasma into the tissue. So that's the part that we measure, the liquid. Plasma, by the way, is very similar to seawater. Really interesting. Another story. Okay, so this is called C sub T concentration in the tissue, T for tissue. And as we said, this is a linear system. We're going to have an impulse response function, H. And our input curve C, the curve in the plasma, that's going to drive the tissue. That's our convolution operator. Okay, so that should be that same operator. And what we learned yesterday was the compartment models that the impulse response is the sum of exponentials. Two compartments, two exponentials, one compartment, one exponential. And of course, all of the money, all the reason we're doing it is we can imagine taking this data, measuring that, figuring out the impulse response, and getting the rate constants, and then using some algebra, getting the terms of the exponentials, using some algebra to get back to the rate constants. All right, let's start with this. Model number one, simplest model. Start with the plasma, there is plasma. And we're going to call the rate at which it goes into the tissue K1, and the rate at which it clears K2. Now hopefully you remembered yesterday and you said, wait a minute, yesterday he was doing K12s and K31s and things like that. And if we had a lot of compartments, we would do that, but the PET models are so simple that it just isn't worth double subscripting them, okay? Even though officially we're supposed to. Okay. So we'll call that K1, how much it goes in. K2, how much it goes out. Okay, here's again our input function. Here would be the units. It would be in becquerels per milliliter. We might take blood samples. Count it in a gamma counter, per problem one yesterday. Turn that into sensitivity of becquerels per ml. The scanner, we hopefully calibrated it per lecture 3. Becquerels. You know why I did this? ml and centimeter cubed? Isn't an ml, that's a milliliter. Why did I do that? Exactly, that strictly if we take your blood out, it's a liquid and we are measuring it per liquid volume. The scanner is per absolute volume, centimeter cubed. So it's a real subtlety there. It's not an important one, but we live with it all the time. Okay, so what's the net flux? What's the derivative? What's the CDT? So the input, K1 times Cp, again assuming linear system, clearance K2 times Ct. Math part's easy. Let's try to turn that into biology. What do those parameters mean? Okay, now we've spent a lot of time on K1 because, you know what, every tracer has a K1. In fact, if we have a tracer without a K1, nothing's going to happen. It's not very interesting, okay? It's not going to be a great tracer. We're going to have a black hole wherever the tissue, because nothing is going in. It won't matter what else might have happened if it had gotten into the tissue. So we always want to care about K1. Now maybe K1 is really important, what we care about, or K1 is just a nuisance we just got to get in to see it. We saw that in the case of the transporter. Let me go back really quickly. Okay, that was a mistake. Okay, so K1 is driving this early stuff, the original delivery, and all. That's why I said they all look the same if they have K1. We're usually interested in the other terms of the model that are going to produce the interesting parts of the image, which is why the chemists spend so much time building these cool, unique molecules. Okay, back to Okay, so what is the biological or physiological interpretation of K1? Well, if I have something in the blood, and I measure what's going on with the tissue, two things have to happen. First, it has to get there, and then it has to get out of the blood and into the tissue. So it's got to get delivered, we call that blood flow, and then a fraction has to be taken out of the capillary into the tissue, we call that extraction. So we describe K1 as a product of two terms, the blood flow and the extraction. Flow would have some units, depending on how we write it, milliliters per minute per, should be centimeter cubed. The extraction is a little more complicated. It'll depend a little bit on the molecule. Okay. And it'll depend on something called the permeability surface area. Let's come back to that a little bit. Okay. Here's a model for a capillary. Okay. Pretty complicated. This goes back to some classic analysis, 1959, 1962, by Rankin and Crone. Came up with some simple expressions for this extraction. So here what they looked at is, let's say I have an artery coming into a little capillary, and then I have some venous blood coming out. Let's call A, C sub A, the concentration over here, and C sub B, the concentration over there. Some fraction of the tracer will be extracted. There it is, the arterial venous difference is a fraction of the arterial. If I have nothing on the venous side, 100% was extracted. If the venous side is completely equal to the arterial side, nothing was extracted. Okay? So that's what they started with. And then they wrote down some partial differential equations for the model of the extraction. They looked at how things flow, they did that with nice unit areas there. They came up with an expression, pretty simple one, it turns out, for the arterial, that you have some arterial values here, and that across the capillary, things decay, it turns out, exponentially. It's a little complicated. It's got a couple interesting terms. It has something called P, the permeability. It's basically how easily the molecule slides into the tissue. Could be because it's a fatty substance that just diffuses. Could be because I have a dedicated protein that sucks it in. Like glucose has a transporter to suck it in. It's going to be a function of the area that you have here, the radius, how much surface area you have. And it's also going to be a function of the flow. When they did the analysis and solved for it and plugged it in, they found out this term for the extraction. I think I've repeated it over here. Okay, I'm sorry, that's hidden a little bit. Let's stay with it over here. That expression, 1 minus e to the minus ps over f. Let's think about that. So I have some value for the permeability surface area. At low flows, this is small, so this is big, so this is small, so my extraction is high. But as the flow gets higher, I love this wonderful triple negative equation, that gets bigger, that gets smaller, that gets bigger, that gets smaller. Why is that? Why is it that as the blood flow goes up, the extraction goes down? Why? What do you think? You're a molecule, you've just arrived at a capillary. Two of you are molecules, one of you are in a high flow capillary, one of you are in a low flow capillary, and the low flow of you is more likely to be extracted. Why? Time. Just spend more time in the capillary. You have a better odds of just getting sucked out. Very simple. Faster you are, you're just flying, as you know. Okay? So we write the K1, it's extraction times flow. Looks like I've heard that's going to be that flow, sorry, times that. Now there's some interesting limiting cases here. What if we're working with a molecule with super high permeability? Much, 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 much higher than flow. So if this is really, really big, this is e to the minus big number. At that point, the extraction will be 1, or nearly 1. And K1, since it's flow times extraction, will equal 1. PET blood flow studies, there are no such thing. There are PET K1 studies. And if we assume that this is true, then we cross that out and say it's a flow study. Okay? So there's no such thing as a blood flow study. Now we use, for example, oxygen-labeled water as our blood flow agent, and we assume this is true. And in some organs it's pretty good, really good in the heart. It's pretty good in the brain. Not perfect. There are actually some molecules that get into your brain better than water. Any ideas what they are? This is a molecule that probably many of you have some experience with. Alcohols get in the brain really, really well, better than water. And so if you really want to measure flow in the brain, you label alcohols. All sorts of them. It's really wonderful. Okay. Now the other case is interesting. It's one of my favorite facts in this lecture. Okay. The reverse would be, what if I have something that permeability is very poor? Some molecules need help getting into tissue. It really depends. It could be large, it could be charged. And if the flow is much greater, and you plug that in, so if this is much greater, you can do a Taylor expansion. At that point, K1 is equal to the permeability surface. Now you're looking at that permeability. And that might be interesting. But the vast majority of cases, you're somewhere in between. All right, so to summarize that one, it's a simple first one-compartment model. There's our differential equation, K1Cp minus K2. Here's our solution, the convolution equation, in the scary form and in the less scary form. And we did this part yesterday. We talked about that, we thought about that convolution as if we had done these separate injections. And if I gave a single injection, it would come out like this. Can I physically do that experiment? Say I was studying the brain. Say this was my model for the brain in a tissue. Is there a way I could have done this experiment to truly give a perfect bolus to see that impulse response? Is there a way to physically do that? To give a perfect bolus to the brain? Well, I would need a volunteer. I would need somebody who's willing to have their carotid arteries catheterized. And then we inject right up the carotid artery. Oh, we might have to tie off the back so nothing comes back around again. And if we could do that with a little drop of radioactivity, like that, we could measure exactly this. This has been done in monkeys. They don't do it in humans, thankfully. But you can do that. You can measure it this way. That's how we learned it worked. And of course, if we gave a second injection, we'd see that. We saw all that part yesterday. Now, really what happens when we're nice to people and we inject it in the vein, really we get a continuous curve. We get a curve which, of course, we can model as a bunch of different injections, individual ones, each of them producing an exponential response. That same simple model that we're doing with food. So only you know that really when we see these nice curves, we're really seeing sums of exponentials of each of the independent delivery. All right, good. A few more minutes. Let's do a little play with some of this stuff. I'm going to show you some of the exercises we use at this course. That just to show that we have those, be able to do that. And we'll bring it up and talk about some of the ideas that we've just played with, convolution extraction, and the models and the rate constants. And down here, those are that information that's available to you there. So let's go to the course, to that one, and so here's the exercise on convolution. So I'm going to start with the case where this is going to be my input function, C sub d concentration in plasma. Okay, it's going to drop as a function of time. I'm going to have, here's my impulse response, happens to also be one exponential. That was the case we talked about yesterday. An exponential input and an exponential clearance. Okay, let's see if I can do it. Okay, so let's start. Oops. Okay, so initially I delivered the red molecules, and we got some red in, and now if I deliver the next one, okay, so the way this picture is working is it's reflecting the fact that, well, at time point 2, it's two colors now. We have, if you imagine that I could give you red molecules in the first minute and then orange molecules in the second, and then measure back the colors at the end, I wish I had that machine. Then this would say, well, the red I gave, and they're going to clear away as an exponential. I just added some orange ones. Now, the orange ones were smaller because I gave less. Okay, let's add another color. Okay, now I've added some yellow ones. So my total is a combination. I have some tracer that I gave 2 minutes ago that's had 2 minutes to clear. Some tracer that's given 1 minute ago, one minute to clear. Some that just got there. But they're all combined. They're all convoluted together. Okay? And as we go over time, of course, what we measure is this total. which is the difference of two exponentials that we're seeing in that final curve, but it's just a function of how those things break down. Okay, let's do this a little differently. Let's now make, instead of the input being an exponential, let's make it be a constant. Okay? So instead of single strength, just hook you up to a pump and keep it going. Now let's watch what happens. Same impulse response. You know, this is the same person. All I've done is I'm repeating the experiment now. A minute ago I gave you a bolus. Now I'm going to hook you up to a pump and have it constantly infused. Okay? The person isn't changing. The tissue isn't changing. Before we got a curve that went up and down. See what we get now? Same equation, just different input functions. Okay? We'll start. Okay, first minute, same kind of thing. Okay, let's go on. Okay, now again I'm adding more. You notice my input curve is staying the same. So now what happened? Okay, well I have my, you notice this is dropping with an exponential, the first part. The orange, if you pull it apart, dropping. Every time everything I'm giving is dropping with an exponential, but what I see is a total that's going up and reaching a constant or equilibrium value. So even though it looks constant, however, really everything's changing. New tracers coming in, old tracers going out. I'm constantly redistributing my colors. If I wish we could see these things, this would be very, very valuable. Okay? But it's really letting us take that apart in a way, just to think about that. When it's a constant, it's really a dynamic equilibrium. Things coming in, things coming out. Same equations, simplest equations, things you learned in your first differential equations class. And I can do it either way. I'd have a choice. I have a design choice. Both systems, the bolus decision or this infusion, give me different curves, but underneath I'm interested in the impulse response for this tissue. And I have a choice to design how I give it, how I can do it, which is going to be better to be able to measure. It may depend on which molecule I want to measure, which parameter, K1, or the clearance. We haven't talked about that one yet, which one that means and how to do that. But it's a great choice that we have if we can understand that. You can also see that how long it would take. You know, the speed of getting to equilibrium will be a function of, well, how fast the impulse response would be. If it was slower, this would take longer. And we can understand those characteristics by doing that. Okay, let's do another one. Let's look at extraction. Okay. This is that same curve there. Okay, so here I'm plotting that relationship we just had. Extraction there. This is against blood flow. This would be the total K1. Here's the extraction. So let's, and this is, we get to be God here, so I get to make my tracer be anything I want. So let's make this tracer not quite perfect. All right, so here I have one tracer that's very permeable. He has product of 2, and over this range of flow, I'm pretty linear in there, my K1. Here's another tracer with a different lower permeability. All right, so this is one that if I was measuring, I could measure K1. That's the variable I can get from the PET. And in this case, if I knew this was true, I'd be comfortable that K1 is equal to flow down here and nearly equal to flow up there. And that might be, again, one of those little bit of inaccuracies on that dartboard I'd be willing to live with, especially if this molecule was easy to make and cheap. Okay? Might be very expensive to go from this to that. That might be a very expensive difference to make a different molecule that had that much better permeability. Now, one thing to worry about is that curve. Right now, we have a fixed range of extraction. Flow rather. Different organs have different amounts of flow. Some organs have much higher flow. Or if you're dealing with the heart, well, sometimes you've heard of them doing rest and stress scans in the heart. You do a rest scan, and then you're doing some exercise, you get a drug. What happens? Your flow goes up. So this could be pretty misleading. I might have a tracer that's great at rest, but it might be awful. It might look like that. Stress just because I'm going to a much higher flow. We're looking at the ratio of flow. If flow gets very, very high, the assumption might not be good. Something we want to think about. Take that into account. Just to understand this interesting and complicated relationship. Let's do one more. Let's It's just a nice tool to play and simulate with different models. And what we have there is it's got built in some information. Let's walk around it. So over here we picked a few tracers. I'm going to pick one called FMZ. FMZ stands for flumazenol. It is a molecule. It's like Valium. It's a calmer. It's called benzodiazepine. It's just a relaxing agent. And when we give flumazenol to people, they don't relax because we're giving it at tracer levels. We're not occupying it. Okay? We can have a choice of how we're going to give it as a bolus or an infusion. We'll leave it as a bolus. And we can look at what happens in different parts. Let's see if I can scroll. I think I can get this scroll. Let's see. There we go. Okay. All right. So I can pick a given tracer, and now we have our choice of kind of, well, let's see if we can guess what the parameters might be. Okay, this is a model that, let's just do that one compartment model that we talked about. Okay. So that we have, this is our tissue, and we have an inflow of K1 and a clearance of K2. Two parameters. There's more we have on the model, so we'll just start with that one. That's that one model up top. And I can control that stuff. So what we're going to do is if I take this, okay, so by clicking on it, it has produced the curve. So what has it done? It's took this input function, which is real, and it took the parameters I said, K1 of 0.23 and K2 of 0.2, and it simulated a perfect curve. It solved that convolution equation for us. That's that curve. This curve over here called the residuals is plotting the difference between the measured data, this perfect data, and the curve. Do you think I have good values for K1 and K2? Did I have it? Is this the right values? K1.23 and K2 of 0.2? Well, no, because my curve is nowhere near the real curve. Help me out now. What should I do? I'm going to play with K1 and K2 to get a closer description of this. All we're doing is taking that convolution equation, K1 e to the minus K2t convolved with this input curve. My goal is to match, this is the measurement. How did that scale? Right? This, by the way, we were nice. We didn't even turn on the noise. I mean, I could be mean and make it noisy, but we're not going to go there. I mean, we could do that, and it would be a little worse, but we're not going to do that, okay? We're going to do that. Okay. So what should I do? How can I make a curve? This is where I'm asking you to not depend on the math as much. To try to think about what these rates do and how they're going to produce the shape of a curve. Okay? So I've got K1 and K2. What do you think I should do to try to make this red curve? You know, as I adjust this, it's going to move. And ideally, I can get it to, if it is true that this is one tissue compartment, I can get it to describe that data well. I don't know. But what should I do? Should I make K1 higher, K2 lower? Okay, let's start with K1. Who wants me to increase K1? Who wants me to decrease K1? Okay, I got one for increasing and one for decreasing, and a lot of things that leave it alone. Do all you want to just play with K2? Let's start with K1 just to see what it does. Okay, let's start, see what it does. This is a toy, you can play with it, okay? All right, so I'm just going to say I'm going to just take my K1. What's happening when I change K1? It's increasing, and in what way is it increasing? It's scaling the whole curve. K1 is a scale factor for the whole curve. If we think of that, the impulse response was K1 e to the minus K2t convolved with the blood curve. This is a constant out front. I can just increase it or decrease it. K1 is a scale. And K1 is also the only thing that needs me to be calibrated, because if I have tissue, this is in plasma from blood, that's from the tissue. This defines the calibration. If my calibration is off, K1's off. K2 doesn't matter that much. All right, so we've got part of this. So let me get it. Let me make K1 up and up. So I get the, let's just get to there. Okay, so I got the beginning about right, but obviously the end part is not close. Do I want to make K2 is the clearance rate out of the tissue, do I want that to be faster or smaller? Do I want it to be bigger or smaller? Smaller, right. It's clearly too fast. It's just going out of the tissue too fast. I need K2 to be smaller. See what we can do? Like, click. Oh, wait a minute. It looks like I've got to change K1 also, because now that's got to, let's get that back there. Still need K2 to be smaller. Oops, got to get my mouse in the right place. Oh, we're getting close. Pretty good. It's not perfect. We're still a little off at the beginning. This is the difference. It's pretty good. Let me see if there's a button to say, review. Let me see the button. Let me see the right answer, because this is created data based on the real true values. Okay, actually this is a 2-tissue compartment model with it. It was very close to that one. It was a pretty good fit with the one, not perfect. Okay. Let's do this one more time. And I want to make it a little harder. Now that might be the curve you might get because you didn't inject much radioactivity. That could be the curve you get because you're looking at a very small region of interest. The smaller the region of interest, the more noisy. Still got a curve to it. It's really not substantively different. Still goes up, comes down. Let's try that again. So let's go. Get rid of 4 hours. I want to go back to that 1 again. Anybody remember what the numbers were we had? This was, whoops, that's too much. Not quite there, pretty close. Here's my residuals on the left. And we'll spend time on that tomorrow about that, trying to vary that variability. Because this is describing this part of the curve a little bit off at the beginning. I got you there. How many of you would like to do this manually on every curve that we got? Keep in mind when we want to do this on every pixel, we might have 10,000, 100,000 curves. We don't want to do that. The next lecture, we're going to solve that problem in terms of how we estimate those parameters. But you see, it's a backwards problem. It isn't a matter of saying answer equals data. We have to find those values that come. Okay, thanks.